Right then, so experiment time. So on the bench, scooting closer, we have our signal generator, and it's at 3.6 gigahertz, which a lot of UK 5G telecommunication systems operate at. You don't believe me? Just bloody Google it. Ofcom 5G. Don't listen to the idiots. Okay, we have a tri-field meter. Now, what I've done here is I could have basically used my spectrum analyzer and, basically monitored how my dielectric constant, relative permittivity, my skin, my water content, my blood, muscle, bone, etc. Did that between the 2 points. But no, what I'm going to do, I'm going to use their weapons against them. I'm going to use the tri-field meter, the TF2. I'm going to show you how a signal generated can be attenuated by the human body, this magical thing. So there's going to be a lot of photons, or a lot of photon density coming out of here. This, by the way, is a really, really high gain antenna, and it's directional as well, which is really key and important to this. And we're going to aim at this, and then what I'm going to do, I'm going to introduce my hand in the middle, and we should see basically how the dielectric constant of human skin attenuates signals. I'm going to recreate this as well with pig skin. Not been to the butchers yet, but usually those guys just chuck me pig skin, like no charge. But yeah, so pull out a bit. This is our test setup. I say I was going to use a spectrum analyzer, but I don't need to, because why, when the thing in question that's testing all these frequencies is the tri-field? So why not use the tri-field? Why not use their weapons against them? So hello. So yes, we have our tri-field TF2 meter. So this is without the signal generator on. As you can see, this is probably the kind of interference we might see. Although, yeah. Okay, so this is our signal generator set to 3.6 gigahertz, which is around, some are 3.2, some are 3.6, some are 3.8. So I've looked at it as a centre frequency of the UK's 5G networks. Cool, so directly in front, the antenna's there. Right, 3, 2, 1, and let's generate our signal. Okay, that's clearly off the scale. Now watch. So we're still getting our Wi-Fi interference, our pulse. And remove the relative permittivity of my bones, skin, muscle, blood and water content. And again, introduce it. You see the pulse is the Wi-Fi behind. There's nothing I can do about that, because that's an omnidirectional antenna, so that's basically everywhere in the room. But the directional antenna in front, which is really powerful by the way, so the dielectric constant, or relative permittivity, of my flesh and bone is attenuating the signal away. So if you look at the thickness of that and compare that to, say, how... turn that off. So if you look at the thickness of my hand, that bit of the palm there, where the antenna was resting against, and then you can actually, hold on, tools, cool. Excellent. Okay, so let's take a measurement from that. That is, yeah, that's about, get that, oh, you can see that there. Yep, so that's 25 millimeters, which is about the injection site depth, to be fair. Get it over again. Yeah, 25 millimeters. So pretty much completely attenuated. In fact, I'll just turn that off, and just to prove again. There you go. So within 25 millimeters of water, which the water's the biggest thing here, and the muscle as well, the protein fibers, they're even, say, not so much. I suppose a dielectric constant of about 50. Water is about 80. Skin is around the 40 mark. I mean, bone is like 25 or something like that. So it's quite obvious that we can attenuate quite a powerful signal. So there's a high power density there. What's that, like 200 millimeters? And I attenuated that signal off relatively easy. In fact, let's try for the Wi-Fi. I'll get that so you can see it. There you go. So even the Wi-Fi, which is not as powerful as that 3.6 gigahertz signal, even the Wi-Fi, I can attenuate off with my flesh and bone. So this begs the question with 5G, and especially the people who say that there's a nanometer antenna inside you that's transmitting Bluetooth. How's that signal actually getting out of the skin? I mean, this is a USB-C connection. This is, capable of 3 amps of energy, effectively. The draw's probably not that with this when it's powered on, so I'll probably be looking at it's drawing an amp, maybe. So like that's a lot of energy, and that energy, to conserve that energy in kind of a battery mass, would be about like that big, something like that. So that kind of square area. In fact, I've got a better demonstration of that. So that battery is around about 1900 milliamps or 1.9 amps. So possibly that much. I mean, you're not going to fit that in your arm to power that unit, but that's per hour. So you can imagine like what it's just going to get an hour of use. So if you want that for any considerable amount of time, you're talking a battery this big. And bigger, to be fair. So this could probably power that kind of power density needed to get through the human skin. Because don't forget, like, if we're talking about, say, kind of like a Bluetooth MCU or a BLE, which the giveaway is in the name, Bluetooth Low Energy, this battery alone could probably run that for about a month. Actually, probably longer in low power mode if it wasn't constantly sending data packets back and forth, and it was just awaiting a transaction or a pairing or something like that. It was just sat there on standby. Whereas, well, they're out in the wild, these people, with, kind of these meters and mobile phones and stuff, and these things apparently are constantly broadcasting. Well, it's going to tear through that battery pretty bloody quickly, isn't it? So, again, I'm going to do more about the dielectric constant of human skin and relative permittivity, and how signals are attenuated. But effectively, the water in my skin, which is probably even more so today because it's bloody hot, the water in my skin alone would be enough to attenuate that signal. So it's kind of without going off in a tangent, I'm just going to make this video X amount of minutes longer than it should be. It's all bullshit, isn't it, really? We know that the human body can attenuate a signal really easy. I mean, just that part of my hand. And you've got to think as well, you know, there's not a lot of muscle structure in your hand. Whereas in the deltoid, it is all muscle. And it's a lot more water than what's in there. And obviously, you know, you can... I've not got a torch to hand. Anyone who's ever done it, a bright torch, you can see through pretty much your hand. You can see your bone structure. Well, not all the bone structure, but you can see some of your bone structure just with a really, really bright light. And it's the same for the signal, really. Well, it's not the same, but it's similar as, you know, it's photons, etc. But if you were to stick a bright light in your armpit, you won't be able to see it through the deltoid muscle. Effectively because it's attenuating the light source off. And it's very similar, but not the same to what it would do for the photons in a radio frequency. If the power density was upped to get through the deltoid muscle, what you would experience is a mini microwave in your shoulder, which would be unbearable. And we're talking some serious wattage in terms of microwave energy. So if anyone wants to try this experiment at home, please do this with a gammon or ham you're going to cook. But get yourself a gammon or ham, and before you cook it, just for a couple of minutes, put it inside of your microwave on full power for 2 minutes, say. Take the gammon out and make an incision into the gammon. Now, I know you're going to lose a lot of juice and a lot of, you know, moisture and cooking and stuff, but in the relevance to the science here, it's maybe a worthwhile sacrifice of one of your Sunday dinners, maybe? Don't know. But then cut through it, and what you'll notice is the microwave energy has cooked the meat from the outside in. Now, there's a popular misconception, because microwave energy, when it transpires to cooking food, vibrates the water molecules from the outside in. The popular misconception is, because it vibrates the water molecules, it is effectively heating from the inside out. Technically true, but actually false, because it's, instead of the infrared energy from your oven, for instance, from the heat penetrating and basically turning the water into steam, what's happening here is the microwaves are vibrating the water molecules and turn them into steam from the inside out. Whereas the inside of your ham for 2 minutes in the microwave will be uncooked. The outside, you'll notice how it's slowly creeping in. And in some cases, when you cut these hams in half, you can actually see the microwaves, well, the path the microwaves have taken. So they'd be like maybe triangles on the corner if it's a square ham type thing. But try that for yourself if you don't believe me. Microwaves, in fact, cook from the outside in. It's just basically they impart their heat by vibrating water molecules, and that vibration of water molecules creates steam. The steam imparts its heat as thermal energy into the meat, as opposed to the infrared energy imparting itself as thermal energy and boiling the water off that way. But anyway, it's been a bit of a tangent, I know, but yeah, it's basically, it's busted. Like, there's no way a signal can get out from your skin, and there's no way a signal can get into your skin, at these power densities anyway. So, thanks for watching the video, and I'll catch you in the next one.